Okay, so now we're ready to explain ion formation. Earlier in the semester, we said that um, atoms in group 1A are always found in nature when they form ions. The ions that you get from these atoms are always found in nature to have a positive one charge. Like, for example, sodium ions in nature are always found with a positive one charge. Why not plus 2? Why not plus 3? Why not negative 1? Okay. Group 2A, on the other hand, are always found in nature with a plus 2 charge. If you find ions of group 2A, like for example magnesium, it's always found in nature to have a plus 2 charge. Similarly, atoms from group 7A, if they form ions in nature, the ones that you find in nature will always have a negative 1 charge. So for example, fluorine is always found in nature to have a negative 1 charge if it becomes an ion, fluoride ion. The answer to this question, we can now explain this. Okay, the answer lies in the fact that behavior of the atoms, properties of the atoms, depend primarily on the valence configuration, and the pattern that we see here is that um, the um, the atoms, when they form ions, they have a tendency to achieve a noble gas-like configuration. So there is some kind of stability that's associated with being able to form ions that have a noble gas-like configuration. Okay. Now, why are atoms in the same group? Why do atoms in the same group have the same behavior? Because they have the same valence configuration. So, for example, all group 1A atoms like lithium, sodium, potassium. Okay, they have an S1 outermost configuration. Their valence configuration is S1. By losing that one electron, they all gain a noble gas-like configuration. Similarly, group 2A, like magnesium, okay, beryllium, they have a valence configuration of S2, 2 electrons in the outermost shell, and so they have the tendency to lose those 2 electrons and give you an ions with a charge of plus 2. But why does it stop at 2? And why does sodium stop at 1? Okay, as in group 1A. And group 7A, by gaining 1 electron, okay, they get a noble gas-like configuration of S2P6. But then again, the question is, why does it stop at the noble gas-like configuration? Why not more electrons after that? Let's see. What is the electron configuration of naturally occurring aluminum ion? Let's see, aluminum's over here. So you would expect, okay, so what's the electron configuration of aluminum? Neon core. After neon, you do 3s2 and then 3p1. It's in the p block, right? This stands in p1. So what's the electron configuration of aluminum ion? Well, you would expect it to be isoelectronic with a noble gas. It will be positive. It's a metal. And so it will be isoelectronic with neon. So the answer would be